Alright, hey everybody. This video is a few days late in coming, I know, but, you know, having the flu will do that to you. But anyway, actually I want to start on this page and give you a few notes about some lingering issues. The lab, we will be spending time in class, a little bit of time in class when we get back, with the computers in the lab, making sure you have the graphs you need and everything you need from the program, uh, and are able to put that into your report. But the reports will be due that evening, so work on your report, do what you can, everything you can in the meantime without that, um, so that you can have it ready and just sort of put in the data, touch up your report and your analysis that night, and submit it. Secondly, anyone who needs to take the test because you missed it and couldn't figure out a time with me to take it, or if you need to use your extra time on the test, please email me. There are a number of you, and it's difficult to keep track of everyone. So please just shoot me a quick email letting me know if you need to take it entirely or simply finish it. And that way I'll just have a list of everybody and we can go from there. Okay, so the new topic to talk about is momentum. Now I'm not going to mess around with discussing momentum and sort of deriving where it comes from. I'm just going to kind of give you the equation. We're going to go from there. Okay, so here's the equation. Let me get my pens here. The equation, okay, momentum is represented with a lowercase p. We can talk in class about why it's p, but it's really just because there weren't very many other good letters. P, okay, and it's equal to mass times velocity, and it is a vector quantity. Now, why do we talk about momentum? Why is it a useful quantity to discuss? Well, first off, when we have things that are moving, we can talk about them in terms of acceleration and velocity and displacement. But I think we could all agree that there's a big difference between a mosquito moving at 10 miles an hour and an elephant moving at 10 miles an hour. From a kinematic standpoint, the kinematic equations, those two would be identical in every calculation that we could do. So we need something that includes the idea of mass. Well, we've also talked about kinetic energy. Isn't that something that involves mass and motion? Well, yes, of course. But that, remember, is a scalar quantity. And as such, has some limitations. Now, we found some problems where it actually was easier to solve in terms of kinetic energy and work and things like that because it's a scalar. We don't have to worry about direction. But again, that limits us. So momentum is a more sort of all-encompassing way to talk about motion, and it's actually a much more fundamental quantity, as it turns out. The conservation of momentum is one of the most important laws in physics. So to just give you a quick primer on what momentum is like, let's compare the momentum of two objects. Okay, football player running forward. Right. Let me actually use a good arrow here. Okay, football player running forward with some velocity, and we'll compare that to a bullet with what is presumably a much larger velocity. Let's start with the football player. A running back or a big running back or a linebacker might have a mass of 115 kilograms. It's about 250 pounds. That's big, but certainly not ridiculous. And they could probably run at a speed of about 6 meters per second. Now that's absolute full speed, but sort of still kind of realistic. So what would the momentum of that football player be? Well, it's a pretty simple calculation. Momentum equals mass times velocity. 115 times 6 is 690. Now, units of momentum. There are no fancy units specifically made for momentum. The momentum units are simply what goes into it, kilograms times meters per second. Okay, so football player at full speed, 690 kilogram meters per second. Now compare that to a bullet. Okay. Now, which one's going to do more damage when it hits you? Okay, the bullet, obviously. But is that an accurate representation of what the momentum is? Well, let's find out. The mass, this is I guess it's a Tommy gun, but so for a submachine gun like this, an AK-47, something like that, what we're dealing with generally is about an 8-gram projectile. Okay, so 0.008 kilograms. With a muzzle velocity of about 715 meters per second. Okay. So, what would be the momentum of the bullet? Well, again, for the simple calculation, mass times velocity. It comes out to 5.72 kilogram meters per second. So, it's not just that, okay, the linebacker has more mass, so it's going to be slightly more, it's a lot more momentum. Okay, from this standpoint, the linebacker has a lot more momentum. Okay, and as I said before, momentum is a vector, so there is a direction associated with it. So I suppose in both of these examples, I used to the right as positive because I had a positive velocity and a positive velocity. Okay. Now, where this becomes more powerful is when we have a collision take place. Okay, we've not had any way so far to deal with two distinct objects moving at separate velocities colliding with one another. Okay, so I'm going to show you an example of that now, but I don't have it set up, so I'm going to pause. But it'll be instant for you, so hang on. And voila. So I've turned the screen sort of green, so we have a pool table, right, into a couple of billiard balls. And for this particular problem, I'm going to confine everything to one dimension. So everything can only move left or right. I'm not going to allow anything to move up or down just yet. Although you can imagine how to expand the problem from there once you've seen that. So these are billiard balls, so they would have the same mass. We'll talk a little bit. A cue ball has a slightly different mass, which is how the ones you pay for know when you scratch to send that one back to you, as opposed to the other ones when you make the ball, they put it away and you don't get it back. But anyway, all the other balls are the same mass, but these two would have maybe two different speeds, so V1 and V2. Oops, I made the ball V2. V1 and V2. All right, so the idea of conservation of momentum, as you might imagine, works a lot like the idea of conservation of energy. Conservation of energy was essentially the change of energy of the system must equal 0. Now, there are a lot of different types of energy, so what we said is change in potential plus change in kinetic equals 0. And this had the sort of asterisk next to it, which said no non-conservative forces may be acting. Okay, so we had to only use this in places where there's no friction. Well, as it turns out, we don't have that restraint with momentum. It's easier without friction, as most problems are. But it's not necessary to constrain ourselves and say it only works without friction. So, conservation of momentum basically says that the change in momentum of the system is equal to 0. Okay, it must be equal to 0. Okay, in other words, I'd have Once this collision happens, somewhere in the middle here, I think probably somewhere around there, since the red ball is moving faster than the blue ball, our collision happens somewhere around there, we'd have ball 1 would have some change in momentum before and after. Ball 2 would have some change in momentum before and after. And when we add those two together, we would get, of course, we have to get 0. Now, what's tricky about this, rather than conservation of energy, is that this is, of course, a vector equation. But it still equals, not sure why this one disappeared, it still equals 0. Okay. So what we'll end up doing is split this into an x component, if we had a two-dimensional problem, split it into an x component and a y component. But rather than having to combine them at the end, we just set them both equal to 0. Okay. So let's take a look at this particular problem. And actually, we won't go into too much depth. I don't want to solve this problem, so the video is already getting a little long. But here's the last point I want to make, that there are two types of collisions. Okay. If I were to play this out, okay, so I had MV1 initial, actually, sorry, change would be final minus initial. Final minus MV1 initial, okay, that is my delta P1, plus MV2 final minus MV2 initial. Okay, that's just your basic, a change in something is final minus initial. Okay, so I've just plugged in for that. But what you very quickly realize is there are two things in this equation that I don't know. Okay, the two things in this equation that I don't know, if you are paying attention, would be the two V finals. Don't know them. Okay, assuming I was given all the other information. The result of the collision is what I don't know. So either I need to know one of those, or I need another equation that's going to allow me to solve this. Okay, and we can get that information from knowing what type of collision it is. There are two types of collisions, and they each give us a critical piece of information. Okay, first type is called an elastic collision. Elastic collision, an example of that is what you see above here, billiard balls. Okay, the two objects collide and bounce off. They do not stick together. They do not deform. They don't crunch. They don't do anything. They just bounce off perfectly. Okay, and the critical, if it's a perfectly elastic collision, okay, the piece of information we get is that kinetic energy is conserved. Okay, and that allows us to build a second equation over here so we can solve the problem. Okay. Other type, might be able to guess, inelastic collision. Okay. Now this is exactly the opposite. Okay, it's where we have two objects moving separately initially, which come together, hit, and stick together and become one object. Okay, so this would be, for example, two chunks of wet clay that come together. Okay, and stick together. They become one object in the end. Okay. So, the critical piece of information that this gives us is, it's not obvious at first, but it's that V1 final equals V2 final. Okay? If they stick together, they must be moving the same speed in the end. Now, if we bring that information up back to our equation, okay, these two unknowns become one unknown because they're the same thing. Okay, so Elastic collision tells us kinetic energy is conserved. Inelastic collision tells us that the two final velocities must be the same. Okay? All right. So, just to recap, a few notes. Talked about the lab and the test. Okay? Make sure you email me if you need to finish the test. If you don't, you won't be on my radar, and it'll keep getting pushed to the side, and it's going to be harder and harder to schedule. Okay? Secondly, definition of momentum. It's useful because it incorporates the idea of mass into movement, and it's a vector, okay, which allows us to do some more powerful things than we could with just kinetic energy. Okay, mass really matters. Okay, if you are much less massive than something else, you've got to be moving really fast. We'll do a problem where we'll calculate how fast you'd have to hit a ping pong ball to stop a basketball. Okay, and it's, well, spoiler alert, but the answer is really fast. Okay, and then lastly, momentum being a vector, okay, we can set up this conservation of momentum equation, and with a little bit of information about the nature of the collision, we can solve this problem without too much trouble. All right, we'll see you next week.